Now, L'Hôpitaux, this is a French name, so you can often find it's spelled as like hospital, Le Hospitals called. I have yet to ask a French-speaking person how this actually gets pronounced. But I think in both cases there's an S there. Yeah, I should ask Professor Gillant. Okay, anyways, L'Hôpitaux, that's how we usually say. L'Hôpitaux rule. Well, before I explain what L'Hôpitaux rule is, you first have to understand what indeterminate forms are. So what's an indeterminate form?
How you say hospital in Spanish? How do you in French?
That's how you say hospital in French?
Yes.
L'Hôpitaux, okay.
I thought you were saying indeterminate forms. How do you say?
No. This is hospital. All right, indeterminate form. Okay, so in order to explain what indeterminate forms are, I first have to explain what determinate forms are. Okay, if you had limit of some fraction, and you can see that the top will get closer and closer to some number, whereas this one will grow to infinity grow to infinity without limit. It just becomes bigger and bigger. What will be the limit of this? This will be? Zero, because you have a constant value divided among infinitely growing number of people, right? So you have finite resources and you have infinitely growing number of people, then everyone gets zero. That's what this means, right? On the other hand, if you had infinity on top, but then you had some constant on the bottom, what would this be?
Positive.
Infinity.
This will be infinity, right? Assuming that C is positive, right? So these are what we call, these are examples of determinate forms. And these are forms where just by looking at how the limit looks like, you can judge whether it's going to go to zero or infinity or some value. If that's just by looking at it, you can figure it out. Okay? That's called determinate forms. However, think about the following question. What if you had a fraction limit that looked like infinity over infinity? If you divide infinity by infinity, what would you get?
Infinity?
Infinity? Some people say 1. Anything over itself is 1.
I divide.
However, if you think about explicit examples of such, you're going to end up saying otherwise. So here, if you say limit of 2x plus 1 over 3x minus 2, as x goes to infinity. Now think about this. If you plug in infinity, infinity times 2 is infinity plus 1 is infinity. So this goes to infinity. The top goes to infinity. Same thing for the bottom. 3 times infinity is infinity. So this is indeed of infinity over infinity type. But what's the limit? 2/3. It's 2 and 3, so it's 2/3. Okay. What about limit of x going to infinity of x squared plus 1 over 3x? What's the limit?
2x over 3.
No, you're already using L'Hôpitaux. You're not doing that. No. Just by investigating, what's the limit?
Infinity over infinity.
Right. The x squared goes. The x squared increases much faster than 3x, right? If you had x as 1,000, 1,000 squared is 1,000,000, and you're dividing 1,000,000 by 3,000.
So that's like infinity over.
This is still infinity over infinity, isn't
Right,
it? Right?
but it's
This will go to infinity. This will go to infinity. So it's infinity over infinity type.
The one's faster and larger.
Yeah, but the top is a lot faster than the bottom. So if, for example, if x is a million, million squared is a trillion, divided by 3 million, that's still close to a million, right? Yeah, it's a third of a million. So that means that this will be infinity.
Wait, how come the top is 2 pins?
This one?
Yeah.
It's when x is a million, you get 2 million divided by 3 million, about, right? Which is about 2/3. So as x becomes really big, this will be 2/3.
So that's like their ratio.
Yeah, so in other words, these are small players
Yeah.
compared to the big fish.
Yeah.
So these 2x and 3x go against each other and you end up with 2/3. Yes?
So can you think about it in a way that, like, let's say you get rid of the x on the bottom, you take x squared and just have it as x, and then
Right.
you have
So
only
even
one x.
this one, it's
Yeah.
like x squared and 3x are the big players,
Yeah.
and this is like really small compared to the others.
Yeah,
So this is really like x squared over 3x, which is like x over 3.
yeah.
As x goes to infinity, that'll be infinity. Now, can you give me an example where the limit becomes 0? It should still be infinity over infinity type, but the limit is 0. What would be an example of such? Yes?
3 over 3x?
Okay, so this one won't be of this type because if x is sent to infinity, this is still a constant over infinity, so it'll be that type. It won't be an indeterminate. Give me another example. That's like infinity over infinity type, it goes to 0.
X over x squared?
Let's put x squared plus 1, so you can't simplify. So that'll be an example where this does go to infinity, this also goes to infinity, and then the ratio will go to 0 because the denominator goes to infinity much faster.
There's not one that goes to negative infinity, right? Or
Can it go to negative infinity? Well, I guess when I write like this would be like positive, positive, so it can't have a negative value. Okay, anyways, as you can see, what's happening is that we don't know unless we actually work it out. Okay? For these types, when you see a limit that looks like infinity or infinity, just by looking at it, you can't determine what the limit is because it can be anything. On the other hand, for determinate forms, just by looking at the form, you can say what it is. Right? So that's the big distinction between an indeterminate form and a determinate form. Here's another example. 0 over 0 type. So I wonder if you remember this. What's the limit of sine x over x as x goes to 0? It's 1. That's what you learned in Calculus 1, right? This is something that you learned in Calculus 1, right? And this is indeed 0 over 0 type because when you plug in 0 on top, it's sine of 0. Sine of 0 is 0, right? And when 0 is plugged in here, it's 0. So you do get 0 over 0 type, where this limit will be 1. However, say you got sine squared of x over x. What would happen to this one? Well, that's limit of sine x over x times sine x, and this goes to 1, whereas this goes to 0, as x goes to 0. And 1 times 0 is 0, so you get 0. Another example would be like limit x going to 0 of sine x over x cubed. In this case, you have limit of x going to 0 of sine x over x times 1 over x squared, because x times x squared is x cubed. I know that this goes to 1, whereas what is 1 over x squared as x goes to 0? You're dividing 1 by a very, very small number, right? 1 divided by 0.1 is 10. 1 divided by 0.01 is 100. You divide 1 by something that's closer and closer to 0, you get something bigger and bigger. So this will go to infinity. Right? So this will be infinity. So again, when you have a 0 over 0 type, you can't see what the limit is unless you work it out. Okay? So these are called indeterminates. Yes?
Pardon me, that's just the whole, all of them on the right side board, or just the right side of that board? Oh.
So this one is an indeterminate, this one is an indeterminate. And there are many other examples. So some more examples of indeterminate will be something like, what's that? Infinity to the 0th power. What do you think this is? Well, you were taught that anything to the 0th power is 1, right? But the problem is, this number is not really 0, but something that's getting close to 0. If it's that form, and if this is growing to infinity much faster than what this is trying to do to make it close to 1, then you might get a value that's bigger than 1 or even infinity. So that's another type of indeterminate. What do you think infinity minus infinity would be? Well, anything minus alpha is 0, that's what you were taught, but it could be that these two are different infinities growing at different rates, and you might get a different number,
Which you have.
or even infinity. If you're wondering what kind of question would this be, here's an example. Square root of x squared plus 4x minus x going to infinity. Well, you plug in infinity to this one, it is infinity. Plugging infinity here, it is infinity, right? The calculation of this requires some work, but after like half page of calculation, you can show that this will be 2. So there are many kinds of indeterminate forms, but among those, the ones that we need to know for the L'Hopital's will be these two. Infinity over infinity type and 0 over 0 type. Okay, so once you are sure of what indeterminate forms are like, let me state the L'Hopital's theorem. It works like this. Suppose limit of x going to a, or it could be x going to positive infinity or x going to negative infinity. And you have a fractional form of a limit. Is a infinity over infinity or 0 over 0 type indeterminate. And the limit of x going to a of f prime of x over g prime of x, let's say this limit exists. Okay. Then limit of x going to a of f of x over g of x is equal to limit of x going to a of f prime of x over g prime of x. That's the L'Hopital's rule. And although I wrote a lot of things, it's really simple to apply. So let me explain by giving you some really quick, easy examples. Okay, example number 1. let's say you want limit x going to 0 of e to 2x minus 1 over 3x. This is a rather hard question, and you wouldn't be able to figure it out unless you know the following fact, that limit of h going to 0 of e to the h minus 1 over h is equal to 1. Have you seen this? How many of you have seen this before? This. Not many, right? Even when I teach Calculus 1, I mention this briefly in passing. So it's not a limit question that you usually know. Now, if you know this, then the question can be solved like this. You have limit x going to 0, and then e to 2x minus 1 over 3x. You pull the 3 outside as 1/3, and put a 2 here and put a 2 there. Then this is same as that question, right? And then you think of 2x and 2x as h, so that this limit will be 1, and then the limit will be 2/3. So there's a trick of getting this to work if you know this result, but who remembers this? Not many. Okay, so that's not how we're going to do this. Instead, we're going to say, if I actually plug in 0, this is z to 0th power, which is 1. 1 minus 1 is 0. And when you plug in 0 in the denominator, you get 0. So this is a 0 over 0 type indeterminate. Okay? Therefore, you can apply the L'Hopital's, right? What does the L'Hopital say? Differentiate the top. If you differentiate e to 2x, what do you get? E to 2x times 2, because of the chain rule. 2x has to be pulled out and differentiated. And then if you differentiate 3x, you get 3. And now you plug in 0, so that's going to be 2 over 3. Done. So it's a magical formula. You can just calculate the limit by differentiating the top and bottom. Yes?
Wasn't there some rule when it came to infinity with e to the x? I forgot what it was. I think there was like something.
Okay, so you're recalling something about e to the x being going faster than any polynomial.
Yeah.
Yeah. Yeah, but that's not relevant here. Okay. All right. So example 2. Here's a limit of x going to 0 of 1 minus cosine x over x squared. Very standard question in Calculus 1. How do you do this in Calculus 1?
Plug in.
You multiply the conjugate. You multiply 1 plus cosine top and bottom, and then the top becomes 1 squared minus cosine squared, which is sine squared, and then you sine x over x squared times something something. Takes like half a page to do the calculation. Well, you know what? We forgot all that, right? Instead, what do we have? L'Hopital's, right? Oh, wait. Anytime you want to apply the L'Hopital's, what do you want to do?
Determine if it's indeterminate.
You want to know that it's a 0 over 0 type or infinity over infinity type. So you have to plug in 0 to make sure that this is 0 over 0 type, and you must write this. If you forget to write this on the exam, 1 point off every time you forget, okay?
But then how about if you give us a question that's neither, then we just say it's neither?
Then it's not an indeterminate, so you don't have to use L'Hopital's. You can do it in some other way, okay? But this is 0 over 0 type, so we can't use the L'Hopital's, which means you differentiate top and bottom. Derivative of 1 is 0, derivative of cosine is?
But how do we prove it's 0 over 0?
You plug in 0. What's cosine 0?
It's 1.
1 minus 1 is?
0.
0. If you plug in 0 here, 0 squared, that's
0.
0. So it is 0 over 0, right? If it's 0 over 0 type, that's when you can use L'Hopital's. If not, you can't. Right? Okay. So you differentiate the top. Cosine differentiates to
Negative sign.
negative sign, so it'll be positive sine x over 2x. Now you can at this point use the fact that sine x over x goes to 1, but let's say you forgot that. Then you can use L'Hopital's one more time, because this is still 0 over 0, right? Sine of 0 is 0, so this is still 0 over 0 type. So you can differentiate the top, which gives you cosine x, differentiate the bottom, which gives you 2. Take the limit, x going to 0. Cosine 0 is 1, so it's 1/2. And then, let me give you one more example. Example 3. Let's say limit of x going to infinity of 4x squared plus 3x minus 1 over 2x squared plus x plus 7. What's this limit?
4 over 2.
4 over 2, which is 2, right? Because when x is really big, these are small compared to these two guys, right? So it's really these two guys fighting against each other. And then that's after canceling the x squared out, it's like 4 over 2. So the answer is 4 over 2, which is 2. However, let's for a moment that we don't know that, okay? Or we didn't understand what we just said, okay? Then you can still use L'Hopital's. When you plug in infinity, what do you get on the top?
Infinity.
If you plug infinity in the bottom, you get infinity again, so this is infinity over infinity. So you can use the L'Hopital's and say derivative of 4x squared is 8x, derivative of 3x is 3, and this will be 4x plus 1. Okay. It's still infinity over infinity type. So you differentiate top and bottom again, you get 8 over 4, limit x going to infinity, but then this is just 8 over 4, which is 2. Done. So you can use L'Hopital that way. Okay. Let me give you a quick reasoning why L'Hopital works. And I really can't show you all the possible cases, so I'll just do one simple case where we have a limit of x going to a of f of x over g of x is 0 over 0 type. Okay, so if this is a 0 over 0 type, I want to show you that this is same as f prime over g prime. Okay? So how do you do that? Well, first, being 0 over 0 type means f of a is 0, and g of a is
0.
so they're both 0. That's what it means, right? And then we are going to divide the top and bottom by x minus a. You divide top and bottom by x minus a. In a fraction, you can multiply whatever you want to top and bottom as long as you're doing the same thing, right? You can also divide anything top and bottom as you're dividing by the same thing. So I choose to divide top and bottom by x minus a. And then also write in minus fa here and minus ga here. I can do that because this is 0. Right? So since this is 0, it doesn't change anything to put it there. And now look at what this thing on the top is. Limit of x going to a of f of x minus fa over x minus a. Where did we see this?
That's derivative.
That's the derivative. See, this is the value of the function it's the change of the value of the function, right? This is change of y. This top thing is like change of y. This bottom is the difference between the x values, so this is like change of x. So what is this? This is really like change of y over change of x, and as x goes to a, the change of x becomes very, very small. We know that this is a slope, right? Slope of the secant line, but if you take the change of x to 0, this is dy over dx. That's what you learned. So in fact, you learned in calculus 1 that this is same as f prime of a. So look where this gets closer and closer to. F prime of a. And this also gets closer and closer to g prime of a as x goes to a. And that's why this would be same thing as taking limit of f prime of x over g prime of x going to a. Now there's like, my reasoning is not perfect because there is a confusion here, like what if f prime of a or g prime of a doesn't exist? Is it still true that this is right? And that takes a little bit more argument. Okay. But that's like very crude way of showing why L'Hopital's does work.